In this lecture, we will look at the floor planning phase. I have borrowed these slides from this book and from other materials. The main book I have followed is VLSI Physical Design Automation from Graph Partitioning to Timing Closure by Andrew Kang and all. So this is the physical design flow. We have got partitioning, and then floor planning, pin assignment, power planning, placement, and then routing. And in some books, especially in modern books, the phase of floor planning, pin assignment, and power planning are called together as chip planning. So it means the same, chip planning and floor planning. It's just that in some books we call some books specify pin assignment as a separate phase, and some books they club it with the floor planning and call it chip planning. But anyway, at the end of the partitioning phase, we have got the original circuit partitioned into sub-circuits of manageable size, and assigning the shapes and location to the circuit modules uh, is what is the job we have now in the floor planning phase. And we have to have some early estimate of the interconnect length so that the we meet the required needs of the chip in terms of performance. So floor planning can be looked at in two ways. For example, in modern designs, the system on chip designs, floor planning is nothing but placement of all the different IP cores. And you know that an IP core can be a hard IP core or a soft IP core. If it's a hard IP core, the module shape is fixed, but if it's a soft IP core, the module shape is changed, can be changed. And as we saw in the partitioning phase, we were using some of the algorithms to partition the netlist. So we might have partitioned netlists which need to be floor planned. In that case, you're going to have the different partitioned netlists, you may call it sub netlist, as the input to the floor planning algorithm. So whatever is the case, whatever may be the input, whether it is uh, a group of sub netlists or it's a group of IP cores, in floor planning we have to decide an optimum shape for the block. If it's a flexible block, we'll come to that little later. And we also have to decide the location so that the some constraints like the wire length are optimized. So this is what I was saying. At the end of the partitioning phase, you might have them as sub modules, or if you have not started from the scratch, if you're doing a system on chip design, you may just have the IP cores which need to be placed um, such that certain criteria are met. So we have a rough floor plan here with these modules A to E placed in this manner. There is a ground net being routed like this, there is a power supply net VDD being routed like this, and the pin locations are shown here, so we may have to do some interconnections. So this is what I would define as floor planning. Floor planning determines the locations and the dimensions of these shapes based on the area of the module so as to optimize chip size, reduce interconnect, and improve timing. And of course, pin assignment is a step we do after floor planning to assign optimal locations, especially for functionally equivalent pins, so that the overall wire length is minimized. And the power planning step builds the power supply network. We know that all modules need a power line and a ground line, and they have to be routed so that the power reaches the blocks, the VDD reaches the block without degradation. And the results of partitioning and the chip planning phase greatly affect the subsequent design steps. So now I was talking about modules, whether it's going to be a system on chip design um, or a full custom design. We are going to have at the end of the partitioning phase. If it's a full custom design, you're going to have at the end of the partitioning phase the net lists, which are partitioned, which may have to be placed as modules. Or if you're going to do a system on chip design, you're going to have the IP cores. Um, and so we are going to now only talk about modules. So a sub circuit, we will call it as module, and a module becomes a rectangular block after it's assigned dimensions or a shape. Now there can be two types of modules. They can be either hard or soft. And when we say hard block, we say that the dimensions of these blocks, that is the width and the height, are fixed. And for a soft block, the area is fixed, but the width and height are not fixed. So we are going to call that the aspect ratio. The aspect ratio is the width by height, and that can be changed, either continuously or in discrete steps. Now continuously usually doesn't happen, so it can be changed in discrete steps. Here you have an example. So width and a height. Now for all these modules, width into height is area. The area is the same, the area is fixed, but the width and height can be changed. Now we can go to an extreme where we may end up in having an unrealistic or an unreasonable width and a height. So usually there is given constraint on the width and the height. For example, we can have, you can see that Ri is a constraint on the um, width and a height. It says that when the slope is Ri, you have a width Wi and a height Hi, or you can have a height Hi and a width Wi. So you have some constraints. Um, Basically, this is just to avoid the blocks being very long or very thin in the floor plan. So here is just a small example. So you have three blocks. For example, block A has got an area of 4, but it can be laid out like this, having a width of 1 and a height of 4 on the die, or a width of 4 and a height of 1, or a width of 2 and a height of 2. And you may have similarly block B and block C. So now the purpose of floor planning, of course, is a very trivial example, having only three blocks, and A block has got three possible shapes, B has got two possible, and C has got two possible shapes. The purpose of floor planning is to so place them so that you're going to place the area is optimized, and of course the wire length also has to be minimized. So here, this is one possible way you can place these blocks so that the area is now 9 square units, area enclosed by all the blocks together. So first, the area and the shape of the global bounding box is a optimization goal in floor planning. The global bounding box is the minimum axis aligned rectangle that contains all the floor plan blocks, and the area of the global bounding box represents the area of the top level floor plan. And remember that this is the number of, if the floor plan, top level floor plan, is going to have an area of say A square units, then in a wafer, depending on the area, you might be able to place appropriate number of, you might be able to produce appropriate number of designs per wafer. So it is going to affect the yield and the manufacturing cost, and the area also affects the circuit performance, because the more the area, the more the distances between the blocks and more the interconnections, so it's going to affect the performance or the speed. And in certain cases, the aspect ratio, the width by height of the global bounding box also impacts manufacturing and packaging, especially if the packaging and technology is available in say a fixed pattern. So you might have to orient your top level floor plan to suit your packaging at the end of the design. So why are we so concerned about the wire length? Because long connections between the blocks may increase the signal propagation designs, and more the wires, more the capacitance, and if the signal carried by the wire is switching frequently, you're going to have more participation. Wire length is going to affect routability and the manufacturing costs. Let me speak about routability. That's because we have limited routing resources. You're going to have, say, 7 layer process, 10 layer process. So we're going to have a limitation on the number of layers available for routing. So these are the reasons why the total wire length must also be minimized during floor planning. So we would say at this stage, just after partitioning, we would just simply put that the goals, the two important goal, the two fundamental goal, optimization goal in floor planning are that the area of the global bounding box must be minimized and the total wire length must be minimized, and the shape must be appropriate, suitable, or oriented towards the final manufacturing and packaging process, because there are some designs where the packaging requires just a square chip, so the width and the height must be same. So that is just one example of a constraint on the shape of the global bounding box. So how is the wire length calculated? In the floor planning phase, the pin locations are not known. We have not finalized them. We just have the partition blocks, or we just have the different IP cores. If they are soft IP cores, the pin locations would not have been finalized, and so the exact wire length of each net is not known. In fact, it will not be known until routing is done. So what usually designers use is an estimate of the floor plan called the center to center estimate. So we know the blocks and we know the interconnections and we know how many connections are there between the blocks, so that we represent by a connectivity matrix Cij, where the each element in the matrix specifies the number of connections between blocks I and j. And in the center to center estimate, what we are going to do is, supposing you got three blocks, blocks A, B, and C, and you have got, say, 4 connections between A and B. So we're just going to multiply 4 into the Manhattan distance between blocks A and B. So that will give an estimate of the total wire length. This is the estimate, which is it's a very good estimate, which is fair enough at this stage, because anyway we don't know the pin locations on the periphery of the blocks. Okay, so as we said, usually the area and the wire length are the important optimization goals, and we might use a parameter like alpha to distribute the weightage of them. If alpha is 5, both of them are equally important, both area and the wire length, and we have to minimize alpha times area plus 1 minus alpha times the total wire length. The other third parameter, I would say, which is becoming important, third optimization goal in floor planning, is to minimize signal delays. This is especially the case in deep submicron technology, where the interconnect delays are gradually becoming as important as the gate delays. And static timing analysis is used to analyze the interconnect that lie on the critical paths. And so this is something which we should take into account. Let me talk about representations of the floor plans. The floor plans are represented by what is called as a slicing tree. Now, before we go to a slicing tree, we define some terminologies like the rectangular dissection. The rectangular dissection is a division of the chip area into a set of blocks or non-overlapping rectangles. And from a rectangular dissection, we can get uh, what is called as a slicing floor plan is obtained by repeatedly dividing each rectangle, starting with the entire chip area into two smaller rectangles. You can divide it using a horizontal or a vertical cut line, and the slicing floor plan can be represented as a slicing tree. A slicing tree is just a binary tree with k leaves and k minus 1 internal nodes, where each leaf represents a block and each internal node represents a horizontal or a vertical cut line. Let me just illustrate it, then it becomes clear. Now this is what I call as a slicing floor plan. Now what I have it on the right above here. Now if you see here, this is the global bounding box and these are the blocks, and if you see, the entire floor plan can be sliced vertically. In this case, the entire floor plan area can be sliced vertically, and then what is left on both the sides again can be sliced either vertically or horizontally. But if you see the floor plan below here, the entire floor plan, the global bounding box cannot be sliced horizontally or vertically. So this is what we call as a non-slicing floor plan. And generally the slicing floor plans are much easier to handle by the computer. Now why are we interested in this? Because we're going to have so many modules, and so we're going to study algorithms which will optimize the global bounding box and the total wire length. So we have to use computers to solve this problem, and we will see that the slicing floor plan can be represented by a slicing tree, and the slicing tree in turn can be represented by a compact expression called the Polish expression, which the computer can use to manipulate it to improve the floor plan. Now let us look at the slicing floor plan. I'm just showing an animation on how the slicing floor plan So here we have this floor plan on the left, and how can you get the slicing tree? I have a vertical cut, and when I cut it vertically, I'm going to have what is on the left, modules 1 and 2, and 3, 4, 5, 6, 7 on the right. And what is on the left I'm going to cut horizontally, and when you cut horizontally you get two modules, 1 and 2. Now we can use some convention to place them. Say module 2, what is on the bottom is at the left and what is at the top on the right. And what is to the right of the vertical cut, you have modules 3, 4, 5, 6, 7, and again you do a horizontal cut, and what is on the bottom you put it on the left, and whatever is on the top you put it on the right, that is module 3. And again you have 4, 5, 6, 7, again you do a horizontal cut as 4, 5 on the top and 6, 7 on the bottom. So 6, 7 comes to the left here, and 4, 5 will come to the right. And so 4, 5 again you do a vertical cut, and 6 and 7 you do a vertical cut. So this is one representation of the slicing tree. Usually I encourage students to just follow one convention so that they don't confuse and make mistakes. So you can follow something like this. When you do a vertical cut, whatever is to the left you put it on the left on the slicing tree, and whatever is to the right of the cut you put it on the right. Now when you do a horizontal cut, you have to be careful. You can follow a convention like this. When you do a horizontal cut, whatever is in the bottom you put it on the left, whatever is in the top you put it on the right. Is that fine? So I have 3, 4, 5, 6, 7, all these modules to the right here, and I do this horizontal cut. So whatever is in the bottom, it's on the left, and whatever is in the top is on the right. So it is good to follow a single convention so that you don't make mistakes. So this is how a slicing tree can be formed, and a slicing tree and slicing floor plan. So in the next lecture we will see how the slicing tree and the slicing floor plan can be used to optimize the floor plan.